Very interesting keynote there from Lord Willits. He's very kind enough to highlight the issue as a truly global problem, which leads very well into our session now, which is on fostering international collaboration and specifically SDA across the globe. So this was a good opportunity in this session to hear from a number of our colleagues in Australia and Japan, and we've also got someone joining from the UK as well to add to the discussion. So I'm not going to say too much myself because we're already running slightly over time, so I want to leave as much time as possible for the speakers. But we're going to start with Paddy Neumann, who's joining us from Australia, who is the Chief Scientist at Neumann Space. So I'll hand over to you, Paddy, if you're ready.
Hello, Warwick. This is Adelaide calling. How are you doing?
We're very well, thank you. So
good to hear, mate. I take it my slides have come up nicely?
Yes, that looks good to us, Paddy. Over to you.
Fantastic. So, good morning, good evening, good day to you, wherever you might be around the world. My name is Patrick Neumann. Please call me Paddy. I am the Chief Scientist and Head of R&D at Neumann Space. I'd like to talk about in-space recycling for sustainable space propulsion and operations. I'll get to why this is in the international partnerships partway through the talk. So, to begin, firstly, we must set the problem by talking about space debris and space domain awareness before talking about current active debris removal efforts. I know that some of my fellow speakers in this panel session will be talking about similar, so hopefully I do not steal too much of their thunder. I'm especially looking forward to Sudo-san's discussion of what is happening in Japan. I'll talk about this from a propulsion perspective as a propulsion specialist. This is something near and dear to my heart, and how this can be solved by what we're working on, and how it can be applied to active debris removal, and then how this applies to international partnerships. So firstly, space debris. Debris is a byproduct of exploration. This can be fire pits and middens as prehistoric humanity expands across the face of the planet. It could be oxygen tanks on the slopes of Mount Everest, or it could be rocket bodies left in orbit by earlier generations launching hardware into space. This debris population is constantly growing. The more people move around, the more they explore, the more they leave behind. In fact, currently there is more debris than operational satellites being tracked by the various bodies around the world that do this tracking. The unidentified objects are growing quite quickly. These are considered to be fragmentation debris, as well as the result of small collisions. Simply put, these objects are fairly small, difficult to keep a long tracking history on, and thus difficult to backtrack and actually identify what they might be. We do know that they're up there, though. The step changes you can see in the plot at the lower right is mainly due to collisions and anti-satellite tests. The collisions, and be they deliberate or accidental, greatly increase the debris population, making everything more difficult and more dangerous for everyone. The Kessler syndrome threshold density is being reached in a number of orbits, as I'm certain my colleagues will have expanded on previously and will expand on later on. Kessler syndrome is a self-sustaining debris cascade. Once enough shrapnelation happens on orbit, this process can continue creating more clouds of smaller debris that can make an altitude uneconomical to use. You can still launch to it, you can still operate in it, but how long you can operate it there and whether that length of time is worth the cost of putting that object up there to do whatever it is you want it to do, those are different questions. That status for a given altitude could last for decades, could last for centuries, depending on the orbit, depending on what's up there. That's rather odd, sorry about that. So, what are we doing about it? Firstly, space domain awareness. The first part of any solution is defining the problem. With better space domain awareness, we can find out what's up there, what it's doing, where it's going, and we use ground-based sensors to track objects today. such as the United States Space Force and NORAD issuing 2-line element sets, and various other national resources and sometimes supranational resources being utilized to track active satellites, defunct satellites, spent rocket bodies, and the general debris population. In low Earth orbit, objects greater than 10 centimeters across are tracked reliably, with commercial sources improving this so that more people have more knowledge about what is happening and where. Tracking objects enables better avoidance, better prediction, better outcomes for all, in effect, especially if you can track smaller objects so that you know what is happening with objects smaller than what it can be traditionally tracked, but are still dangerous, and do so with higher precision. The more precisely you know something's orbit, the less effort you must put in order to dodge it, and then return back to what orbit you wish that spacecraft to operate in. More confidence, fewer maneuvers, but without active removal, this will still be a losing proposition. Unless you can remove the large objects that can become shrapnel clouds, you will still generate those shrapnel clouds, just at a lower rate. So, active debris removal. To prevent the Kessler syndrome, we must slow additional debris creation, remove debris from risky orbits, and we can do this by mandating and enacting end-of-life disposal. This is being done at a regulatory level. Recently, the US Federal Communications Commission updated their guidelines, their rules in effect, that new spacecraft, you have 2 years to implement this for all the spacecraft designers out there, new spacecraft that wish to use the US as either a launching state or operate in the US and thus require spectrum to use in the US, must be able to make themselves safe within 5 years of the end of the mission. How they do this is left open in very low orbits, and in low orbits you can do this with drag sails. Above a certain altitude, however, you must use an active propulsion system. That active propulsion system can then physically deorbit that object, and for those objects that cannot do this, they must be deorbited in some fashion in order to remove them from the risk profile of low Earth orbit. Removing these large objects prevents them from becoming small shrapnel object that is uneconomical to capture en masse and then deorbit safely. This sounds difficult and expensive, though, kind of because it is. Current active debris removal efforts, in summary, ESA is working on this. Unfortunately, the eDeorbit mission was cancelled due to cost overruns a few years ago. However, they updated the requirements for this mission. ClearSpace won the new tender in 2019, and this will be an initial test of deorbit technology. Astroscale is doing excellent work with the LCD mission on orbit, demonstrating the proximity, rendezvous, and capture operations with well-characterized spacecraft that they designed and built themselves, as a precursor to more ambitious debris removal missions to help remediate the debris population in low Earth orbit. They are being supported by JAXA and the UK Space Agency in these activities. This is a good start, but how sustainable is it? How can this effort be sustained and improved upon? In part, it's difficult and expensive because it's a propulsion problem. Debris removal requires a propulsion system, especially if you want to deorbit multiple targets. If you want your debris removal system, your garbage truck, your trash truck, to go to multiple targets, to multiple job sites, it must have an efficient propulsion system. This requires an amount of propellant, generally quite a lot if you actually run the numbers. Chemical thrusters are just not efficient enough for this mission. There's too much propellant mass required for them to move to multiple targets unless you have a very specific subset of objects in mind. If you do, however, you're running back into the same problem of one mission, which can cost 100 million euro, 100 million pound, and might be able to deorbit a few of those objects. Not a lot of return on investment, sadly. Ion and Hall thrusters utilize expensive propellant. They have the efficiency, but with current geopolitical instabilities, the price of xenon has skyrocketed, as has the price of krypton. So they are less attractive for on-orbit missions today. The solution for this problem requires a propulsion system and a propellant that feeds it that is efficient, storable, easily managed, refuelable, and ideally, the propellant can be found on orbit. Which brings us to my work and one of the reasons why I was asked to present. I am working with my company in Adelaide on a novel propulsion system based on a center-triggered pulsed cathodic arc thruster. It is similar to an industrial plasma deposition system that is used to create thin films of various coatings onto industrially useful substrates. One example is titanium nitride onto machine tools for its friction and wear resistance. To make this work, you strike an arc from a cathode electrode. That arc erodes, ionizes, and accelerates cathode material away from the cathode, and that exhaust is a quasi-neutral plasma beam. It has a narrow, the beam comes out as a narrow exhaust plume from this solid propellant and does not require a neutralizer. Those who are familiar with electric propulsion systems will probably realize I am giving this as a very high level summary. If you're curious, I'm happy to take questions on this one. But this is an interesting way of solving this problem because we utilize solid conductive propellant. Anything that remains solid and can carry a current, we can use as propellant. This includes any metal, although some metals make absolutely terrible choices. Please don't use tin or bismuth. They are just terribly inefficient materials. When using a good choice, the fuel efficiency is comparable to Hall effect thrusters. ISP in ground tests, we have in the 1,000 to 3,000 second range, and we are demonstrating our system in flight next year. As an active debris removal solution, utilizing pulsed arc propulsion systems, we can provide sufficient delta V for the space tug, the junk hunter, the rubbish truck, to go to multiple targets and enact the deorbit process. We can either attach a drag sail and move on to the next object, or more actively dock with the object, maneuver it actively down to a safe disposal orbit, and leave it to deorbit. We can use aerospace alloys as a propellant in our propulsion system. Thus, we can recycle debris into propellant that can be used to move that debris to someplace safe, and additionally harvest extra propellant to take the tug off to the next job site. Thus, you have a use case for in-situ resource utilization and in-space assembly manufacturing technologies. It promotes development of orbital industry and lowers the cost of active debris removal systems by permitting one spacecraft to remove multiple targets, removing hazardous objects, removing hazards to navigation, making low Earth orbit safer for everyone. Now, as far as the international partnership side of things goes, Neumann Space is an Australian company. Australia was the third nation in the world to launch a satellite from its own territory, where it built that satellite itself. Admittedly, that was a rocket donated by the Americans as surplus to one of their test campaigns. It launched from Woomera in 1967. Australia has not done a lot in space since then. And as such, we do not have a lot of the experience, the skills, and the know-how you develop by doing space in Australia. Thus, while we work on our propulsion system in Adelaide here in South Australia, we are working with international partners on the rest of the recycling value chain. Primarily, Cislunar Industries of Colorado are developing an induction furnace to melt and shape these metals so that after the metal is cut, it can be formed into the right size and shape to go into our propulsion system. And then we can use it to take the spacecraft to its next destination. We supported Cislunar Industries as test partner in their phase 1 SBIR using recycled 6061 aluminium alloy, and have demonstrated that other aluminium alloys work just as well as 6061. Cislunar are currently working through their phase 2 SBIR, and we are also collaborating together with Cislunar with the US an instance of Astroscale, as well as others, to bridge gaps and build the recycling ecosystem. To summarize, and I believe I've left plenty of time for questions, space is big, but the useful parts are not. Since those useful parts are getting crowded, we should get the rubbish out of the way so we can keep using the useful parts for things that are useful. This poses a problem until we get the junk out. The problem is they're expensive. If we can make them more cost effective, they become more realistic, they get actuated and brought into reality. Applications of new technology can make the process more economically sustainable so that we have more sustainable operations in low Earth orbit. No single organization has all parts of the solution, and thus we must collaborate internationally to make it work technically. If we wish to make it work socially and politically, we must definitely collaborate with our international partners. Thank you all for your time. I'm happy to take questions.
Thank you very much, Paddy. That was very interesting, and yeah, thank you for braving the time zone difference to join us today. It's very, very welcome. And yeah, I think just in the interest of time and to make sure that we get enough time for our other two speakers, we'll leave Q&A to the end of the session, if that's okay with you. And then if there are any questions, if the audience members keep them in their minds for later on in the session. But thank you once again, Paddy. We're now going to move on to Sudo Katsuya, who is the director of the Paris office for JAXA. And yeah, I'll hand straight over to you, Sudo-san, for your presentation. Thank you.
Yes, can you see my slides?
Yes, that looks good to us. Thank you.
Can you hear me well? Okay. Okay, so good morning, everyone. My name is Katsuya Sudo, and I've been working as the director of JAXA Paris office since 2 years ago, August 2020. And the Paris office, JAXA Paris office, has 2 administrative staff, and so we cover space and aeronautical activities across all of Europe in order to gather information and promote cooperation between Japan and Europe. So today, I'm very happy to make a presentation about JAXA's activities regarding space sustainability in this conference. So my background and major is in law, so I'm not a specialist on engineering or scientific point of view, but try to explain the activities of this field. So first of all, I'd like to show you the JAXA's mid to long-term plan, which is planned for 7 years period from 2018 to 2024 fiscal year. So our plan focuses on 6 pillars, including the 5 pillars that were set as a goal in the basic plan on space policy. And another pillar concerning the promotion of Japan's aviation activities. We have an aviation sector as well. Then the first one is ensuring the space security, and it is able to break down main 3 points. The first, ensuring the sustainable and the stable use of outer space. The second is strengthening capabilities to ensure superiority in use of space. And last one is strengthening the space cooperation with other partners in this area. It's important. These are described in the plan, concretely described in the plan as our top priorities. JAXA has cooperative relationship with about 70 countries and regions through interagency agreements and or the International Space Station program. So regarding the International Space Station, ISS, our government decided to extend ISS operation to 2030, as well as ESA recently, Minister at the Council. So it is good news for us, and we are continuing the efforts to operate ISS and good relationship with partners for that. So anyway, of course, international cooperation is very important for us to implement our activities, and that's why I'm here in Europe. So next, the current collaboration between UK and JAXA. Our president, Dr. Yamakawa of JAXA and the CEO of UKSA signed a memorandum of cooperation regarding aerospace cooperation for peaceful purposes on 25th June 2021, last year. Based on the success track record of bilateral cooperation and the mutual desire to enhance future collaboration, this MOC promotes cooperation between the two space agencies in a wide range of areas, such as aerospace research and development, space science and exploration, Earth observation and satellite application, and last but not least, the sustainable and safe use of the orbital environment. This MOC also stipulates the UK entities approved by UKSA can formulate implementing arrangements with JAXA under this framework. So as its first case, JAXA signed on the same day an implementing arrangement with the Defense Science and Technology Laboratory, DSTL, as you know well, of course, for technical and scientific cooperation on space situational awareness. Please see the right side. The purpose of this cooperation is to clarify the debris distribution around the turf of gravity and to refer to the structure of the gravitation field from the actual motion. Then our action provide both parties with observation data on the same debris. Then bring the result of the analysis for discussion. Like that, with the signing of this MOC with UKSA, so JAXA aims to engage in various collaboration with UK laboratories, universities, of course, and industry partners in order to contribute to the resolution of global issues. I'd like to a bit break down the mutual merit between JAXA and the DSTL collaboration. So DSTL and JAXA are interested in the space debris trajectory analysis using the telescopes. So the best way to efficiently determine the orbit of debris moving in the gravity anomaly zone over the Himalayas is to use data from debris observation from the east and west. JAXA from east side and DSTL from west side are the best pair to carry out these research activities. So you can see the graph in the page, and DSTL has multiple telescopes, of course, you know, in several areas in Europe. And JAXA also have two telescopes described, dedicated for SSA mission. So visible range is here and commonly observable over the Himalayas is longitude 70-80 degrees. That is a good target to share our data. That's why we choose this area for the collaboration. So JAXA delegation, including me, visited La Palma last September to see the telescopes and learn the capability. thanks to very much kind arrangement from DSTL and University Warwick University. So that was, of course, business trip, but it was amazing experience for us and wonderful island. Thank you very much again. And you can see the right side picture, James here. And unfortunately, my face is very small behind everyone, but big smile as well. So thank you very much again. So next in Japan. So you can see the map of Japan, and JAXA headquarters is in Tokyo, east side. And look the north of Tokyo, there is Tsukuba, named Tsukuba. Our SSA specialists are in the Tsukuba Space Center. It takes approximately 1 hour from Tokyo by public transportation. Then the west side of Japan, we have 2 sites for telescope, Ise and Kamisaibaru. It takes 3 or 4 hours by bullet train, Shinkansen in Japan, so a little bit far from Tokyo. Then Bisei Space Guard Center has 2 telescopes, 50 centimeter and 1 meter in diameter, respectively. So they are placed in the 2 independent towers, as you can see. And also the radar system in Kamisaibara Space Guard Center has a dome of 70 meters in diameter. It watches low Earth orbit whose altitude is from 500 kilometers to 800 kilometers. JAXA has many spacecraft in this area. So it can detect objects 10 centimeters in diameter at 650 kilometer altitude. That's our capability so far. So we are very welcome to visit there. Sorry, there are not beautiful coast side, but it is a really quiet mountains and beautiful mountains. It might be a good experience for you as well. So please welcome to the Japan next opportunity. So this page shows the space debris removal. It's also important theme for sustainable use for outer space, and JAXA is actively involved in this area. So as Paris and mentioned last presentation, thank you. So partnership agreement has been signed with a private company, Astroscale. So, you know, based on the Japan, the UK, as you know where. So to carry out a debris removal. Phase 1 will take place this fiscal year with Astroscale, which we will try to get close to the target and take images. And phase 2, scheduled for 2025 onwards, later, will demonstrate capture and removal. The goals of this program are demonstration as well as commercialization. It's a model case for JAXA collaborate with private companies. It's a first, almost a first case to such a kind of activities in Japan, in JAXA. So last page regarding budget, that's always important for us. The budget is approximately 1.5 billion pound, 1.5 billion pound. Euro is 1.7 billion, 1.7 billion, but 1.5 billion pound. You can see it is increasing gradually, even though the pandemic situation since 2019, 2020. We see this trend as strong support from the Japanese government in this field. So, and also I know that the UK government also takes a strong support for the space sector. So let's compete and cooperate together. Thank you very much for your attention. That's my presentation.
Thank you very much, Sudo, and it's our pleasure to host you in La Palma, and we're very much looking forward to visiting JAXA's facilities, hopefully in the new year.
Yeah.
But yes, as for Paddy, I think we'll save Q&A to the end of the session, if that's okay with you. So audience members, if you've still got questions, keep them in your head. And those online, please do continue to enter into the Q&A function. But for now, we'll thank Sudo again and move on to our final speaker of the session, which is Gidon Gautel. I'll hand straight over to you, Gidon, to give you as much time as possible. Thank you.
Thanks very much. I'll just wait to share my screen.
We're currently seeing the program, I think.
Sudo, I think, Katsuya, I think you might still be sharing.
Sudo, I think you need to stop sharing if that's okay. Thank you.
Yes, sorry.
No worries.
Try to stop.
That's brilliant.
It's okay?
Yeah, that's good.
Okay, sorry. Thank you.
Thank you.
All right. Can you see that?
That looks good to me, Gidon. Thank you.
Perfect. All right. Well, first of all, thanks very much for having me here. My name is Gidon. I'm a project manager at BryceTech. We're a consultancy focused on the space industry and other high-tech industries. And I first want to thank Luke Cornwall at the University of Kent for referring me to this excellent event. Luke was one of the finalists in Launch UK's Nanosat Design Competition, which is a partnership between UKSA and the Department for Transport, and which Bryce helped deliver. And all of the finalists in that competition had to consider how they would deorbit their satellites, and the winning design incorporates a novel drag sail design. So it's fantastic to have been invited here through those channels. So I'm here today to, as I see it, essentially give you a bit of a whistle-stop tour of China's space sustainability activities. I should say up front that everything I'm going to present is open source and publicly available. And I hope that essentially the information I present will help provide context to some of the excellent sessions that I can see will be occurring later today. So BryceTech publishes quarterly launch updates, and as far as I can remember, they've generally looked like this recently. So SpaceX at the top and CASC second. And for the last few quarters, that hasn't changed, and I suspect it won't change going forwards. So both in terms of upmass and in terms of spacecraft launched, it's those two at the top. And we've also seen some Chinese launch startups entering the rankings recently as well. In addition to that, both in terms of all satellites on orbit, but also in terms of small sats, China is one of the largest players in orbit currently. And I'm saying all of this because essentially the bottom line is China is a major stakeholder and a major contributor to objects on orbit, and that makes its activities, both regulatory and technical, very important to understand. And in fact, that slice on the pie you can see on the screen will only grow as many of you already know. China has plans to launch its own LEO broadband constellation, the Guoan constellation, which will significantly increase Chinese operated satellites on orbit. So to go through, first of all, the policy and regulatory activities, and this list is non-exhaustive. I'm hoping to just give an overview of the key things to be aware of. First of all, the Space White Paper, which is a good general document to refer to, indicates the intent to strengthen China's space traffic management initiatives, improve debris monitoring and the databases tracking objects on orbit, and to continue to conduct in-orbit maintenance of spacecraft, testing collision avoidance and control, and space debris mitigation technologies. An interesting document released recently to refer to is the SASTIN guidance to small satellites. This gives some pointers on space debris mitigation, stating that satellites should be detectable from the ground, have the ability to avoid collision, and have the necessary capabilities to deorbit promptly. And this draws from previously published national standards and measures, including the administrative measures for space debris mitigation and spacecraft protection, and national standards for the requirements for space debris mitigation, the latter of which is guided by the IADC guidelines for space debris mitigation. In terms of assets, so China has multiple space situational awareness assets, including several large phased array radars across the country, including in Heilongjiang and Shandong province. There's also the Purple Mountain Observatory, or the Zizinshan Astronomical Observatory Sensor Network, which is a network of optical sensors. And China also operates land-based TT&C network, as well as maritime sensors. And there's been some speculation that there might also be SSA sensors operational within that network. China operates the Space Debris Monitoring and Application Center, which was established in 2015, and we've seen multiple missions. Some of the most notable ones there on screen, so including Shijian series of satellites, of which Shijian 15 and 17 observed objects on orbit, and Shijian 21 demonstrated rendezvous and proximity operational capabilities. And there's also been a commercial mission, NEO-1, which was launched recently, which is actually operated by a space resources startup, but whose technology, that is capturing an object on orbit, could be applicable for active debris removal as well. And finally, in terms of multi and bilateral activities on the international stage, again, referring back to the 2021 Space White Paper, China has indicated its intent to continue to jointly address the problem of sustainable development on the world stage, to participate in discussions on environmental management in space, and to open up cooperation in the governments of the space environment with Russia, the US, and other countries and relevant organizations. China is a founding member of the APSCO, which is headquartered in Beijing, and perhaps the most relevant initiative there is the APOSOS network of sensors, which is a network of optical observation facilities specifically for SSA use, with the aim being to host a sensor in every APSCO member state. And once fully operational, the network intends to be able to track objects down to the 10 centimeter range. I mentioned that China's space debris industry standards have been shaped by the activities of the Interagency Space Debris Coordination Committee, of which China is a member. And China is also an active member of COPUOS and GNOSA, and maintains, quote, regular bilateral exchanges on space debris, satellite collision avoidance, and other issues. So I'll close up there to leave time for Q&A, but my email is also there at the bottom of the screen in case you'd like to get in touch afterwards to chat further. Thank you very much.
Thank you very much, Gidon. That's very interesting, and thank you for leaving a few minutes of time for questions now. So I'm going to open the floor first to the audience in person. Has anybody got a question for any of our speakers?
Hi, it's a question for Gidon, but actually for all people who are interested in the Asia Pacific region. My impression is that what China doesn't do very well is communicate in advance of launch what the purpose of their various demonstrator missions is, and then they they're very reticent after the fact to, give many details. So it doesn't instill a lot of trust. They may engage in frequent dialogue. But is there, I suppose what I'm reflecting on is that a lot of the things that we know about China's activities in this area come from commercial monitoring services, observing things that Chinese spacecraft are doing, and then that kind of forces a statement of mission purpose out of China. Is there any way to I don't know, persuade the Chinese to be a bit more open upfront about these things instead of us always trying to find out what they were all about after the fact?
So I suppose if the question is, are there ways to persuade relevant Chinese bodies to be more upfront? I suppose it is an issue, as you state, because the missions I mentioned perhaps also have a national security dimension. I think there's probably not too much I can say on that, but I know that the next panel, in fact, is on space security and space sustainability and the crossover there. And as I'm sure everyone in the room and online knows, the technologies demonstrated are also very interesting from a national security perspective. So I don't want to stray into the ground of the next panel, so I'll offload that question onto them and let the next panel answer it, maybe.
Thank you, Gidon, and thanks for the plug for the next flat panel as well. That was good. Was there any other insights from either Sudo or Paddy there? Otherwise, we'll move on to the next question. Okay, brilliant. We did have a couple of questions for Paddy online. So just looking into chat from Dan Hawk. With the aluminium, are you finding any whisker problems that might impact ARC?
No, actually. We've done some testing. We haven't done long-term testing. We haven't had the opportunity to run a few kilos of propellant through sort of thing. But from early tests, we're not finding any issues with aluminium forming whiskers. Other metals do, which is one reason why we steer away from materials like zinc, tin, and cadmium.
Brilliant, thank you. There was a question in the Q&A. My version seems to show you typing an answer, so I'll move on to the one just after that. So it's a very ambitious mission, Paddy. Curious if your team has looked at techniques to prepare a debris object for fuel use without creating more debris in the process. Also, how do you deal with a debris object that's in a complex tumble?
For the first part, there are some ideas on how to contain it better. So you do the disassembly and processing inside not so much a pressurized envelope, but a restricted envelope. So you bring it inside a shed so that if parts get broken off, they can be contained. As for debris objects that's in a complex tumble, I leave that to the people who are doing the rendezvous and proximity operations side of things, being the very talented people at JAXA. They have the know-how on that side of things. So I'm afraid I'm going to have to kick that one down the can, kick that can down the road.
Thank you, Paddy. Are there any other questions in the room at all? Yes.
Hi, this is a question for Paddy. This is Carolyn from the UK Astronomy Technology Centre. It was just a quick question about your propulsion system. So I was just kind of wondering, do you need to worry about cooling when you have this system? And I was just kind of wondering if you have any ideas of how to implement that.
It's a good question, Caroline. Thank you. All electric propulsion systems will generate heat because you're running an electric current through it. This generates waste heat. If you're doing low power operations, such as what you'd expect for a cube satellite scale system, you can radiate this one away passively, so long as you're not generating too much heat. For larger systems, such as what you'd be looking at for active debris removal systems, you're looking at potential kilowatt scale systems that will generate enough heat that you will need to solve that problem. This is a problem that has been solved in various different ways at different scales by different people. Solutions include using heat pipes to wick the heat away, using solid heat conductors as well, and for more intense requirements, actively circulating a coolant fluid that will dump the heat to radiators. This is something that we have considered, and we do have some plans to do terrestrial testing at these power scales in the near future. We are not at a point where we're ready to integrate for flight these high power systems. Our test launches next year will be at the CubeSat scale. I hope that answered your question.
I'm getting a strong nod, so I think so, Paddy. Thank you.
Awesome,
So I
no
think
worries.
we're running slightly over time, so I'll bring the session to a close there and thank our three speakers once more. And I'm going to introduce our next panel, which will be chaired by Dinsley, and will be on space sustainability and security. So I'll hand over to you, Dins. Thanks again.